Hey everyone! So we're going to start a vodcast, especially for students who are absent, to just kind of get you guys rolling on the ideal gas law, but it also has the Dalton's law and Graham's law towards the bottom. But anyway, one of the things that I do want you to know is that no, you're not going to have a test on Friday, Monday. I decided to postpone that, so that will be now pushed out to Tuesday, Wednesday of next week. Your homework assignment is to get as far as you can on this particular worksheet right here. We will be reviewing it next class. But you should be aware that on your class website, I did post a study guide. So this is Unit 8 website. Down at the bottom, right here, there's your study guide. Now also, I was showing students the warm-up question this morning, and if you want some more additional practice problems on effusion, there's a link, or Graham's law of effusion. Here's a great link for you guys. It shows all of the work and the correct answers and everything to go. All right? Pretty cool. But here we are on this particular worksheet, and we want to look at some of these answers. And so I'm going to start off. A lot of people wanted to figure out how we do number 5. So this is where I'm going to start. And hopefully when I answer these questions, if you have other questions and it's not necessarily about number 5, hopefully I will give you the skills necessary that you could go back and do some of those other problems as well. All right, so here we go. Again, this is question number 5. It says, determine the number of grams. Now, from now on, in gas laws, you need to remember that anytime we're talking about mass, right, mass, we are also talking about, this is equivalent to moles. Because if I give you moles, can you solve for mass? Yes. If I give you mass, can you solve for moles? Yes. We're talking about, mole conversions. So from now on, I want you to think, anytime you see mass, I want you to think about the N in the combined gas law, or the ideal gas law. All right, here we've got some volume, here we've got some pressure, and right here we have some temperature. And the thing you have to see is that minus, okay? Don't forget about that minus. All right, did they give you 2 V's, 2 P's, or 2 T's? No. Did anything change, in other words? No. So as long as nothing is changing, which gas law are you supposed to be using? The ideal gas law. The ideal gas law looks like this. PV is equal to nRT. What is R? That's your ideal gas law constant. Now, we have 3 different values of R. It can be 0.0821, and the unit here would be atmospheres liters over Kelvin mole. This particular number you would use only when the pressure in the problem is given in atmospheres. 8.31, that would be kilopascals liters over Kelvin mole. So we'd use this one when we've got kilopascals. And the third value is 62.3, and this would be when you have millimeters of mercury, also known as torr. All right, so that was just a quick recap of your your ideal gas law. So let's start plugging some stuff in. The pressure in this problem is 1.80 atmospheres. The volume, they gave it to you in milliliters. Ladies and gentlemen, how do you convert milliliters to liters? What do? Multiply or divide? Divide by 1,000. Good job. So you can divide by 1,000, or you can just move the decimal 3 times, because that's what it is. So this would be 0.4506 liters. N we don't have. That's kind of what we're solving for. Use the correct unit for, number for R. We want the one that is using atmospheres. Atmospheres liters over Kelvin mole. Those of you who are crazy about units, there you go. Now the temperature here, we have to be really careful. We need to, you see how in the problem it gave it to us in degrees Celsius? So we're going to take this negative 50.5, all right, and that's degrees Celsius, and you have to add 273.15. Are you guys getting used to that number? Definitely a number you need to memorize, just one of a few. You guys should probably also memorize those 3 values of R. All right, so you got to do that. So I would think that you might be at the point where you're going to start needing to get some flashcards. All right, so our temperature, you know what I like to do sometimes is actually just put into parentheses, like using my parentheses on my calculator. Just throw that in and let the calculator do the math for you. I like doing that sometimes and just rounding at the end. So those of you who, I'm just curious, if you already rounded your temperature When you add this, you will get, let me just make sure I did my math right. Yep. 220, oops, sorry, hold on. You will get 222.65. Did I do my math right? Yeah. Okay. How many of you guys actually went ahead and rounded that 6 to a 7? And so you actually used 222.7, and that would be Kelvin. I would love to compare my answer to yours. All right? I am not going to round to the 0.7. I'm going to keep the 0.65. And you will see why, because I don't think it makes that big of a difference. Just saying. All right, so let's go ahead and solve for n. Boo-doo. I am going to use the 222.65. All right, and I'm hoping that someone in the room uses the 222.7. All right, we'll see whether or not that makes a big difference. All right, so hold on. 1.8 times 0.54506. 0.0821. Okay. All right, let's compare answers. So can I get someone to shout out an answer if you rounded this to 222.7? Can you tell me what your number of moles was? 0.444. All right, cool. And then for me, let me just check my work because I don't think I did it right. 1.8 times 0.4506. There we go. Divided by 0.0821. Let's see, negative. There we go. All right, when you do not round and you use just all of the stuff that was given to you, I get 0.044370.8. What does that round to? Yeah, 0.0444. So anyway, so I just hope that kind of proved to you that sometimes that 0.15 really does not matter on your temperature. If you include it or don't, you're not going to get a significant difference in your answer. All right, but we didn't really answer the problem. All this is how many moles you have. Go back to the original problem. What did they want us to get? Grams of carbon dioxide. Well, if you have moles, guess what you can do? Convert to grams. That's right. So 1 mole, and they gave us CO2, so you need that guy's molar mass. Don't worry, I already did the work for you. It's 44. All right, and I got 1.95, am I right? Grams. And keep in mind, this is carbon dioxide, CO2, but the problem also asked us for another one, so hold on. So the question continues, and it says, determine the number of grams of oxygen that the same container will have under the same temperature and pressure. Hey guys, if I have the same temperature and pressure, will the number of moles be the same? Yes. Yes. So under the same conditions, it doesn't matter what the gas is inside, you will still have 0.0444 moles. It's the molar mass that will change. So if you have a molar mass 44, that'll be oxygen, but that'll be carbon dioxide. But oxygen, it's 16, double it up, 32.0 grams per mole, and so the answer will be just a little different. And so I got 1.42. Do you guys agree? Alrighty, so there was that one. Coming back over here, another problem that seems to stick out for some of my students was question number 12. So I'm going to check out question number 12 for you. Okay, question number 12 says how many grams? Now to me that might mean moles. This is your volume. Let's see, you got atmospheres as pressure, and this dude right here is temperature. Did any of that stuff change? Do you have 2 values of anything? No. So which gas law are we using? Yep, ideal. Okay, so let's plug in what we've got. Pressure 100.0 atm. Volume is 50.0 liters. Don't have N. Didn't really give us that. R, make sure you're using that one for atmospheres. Okay, it's atmospheres, liters over Kelvin mole. Okay, and then the temperature, be careful. They gave you that in Celsius. So you're going to need to do what again? at 273.15. I hope you memorized that number. All right, so let's solve for moles, and obviously, you know, we can't solve for grams unless we have moles. So I want you to remember that when you think mass, think moles. When you have moles, think mass for the combined gas laws and all of that. Divided by 0.21 times 35 plus 273.15. Okay, guys, I did not round my temperature. Let's compare answers. I got 197.635. Now, did anybody actually round their temperature and get a slightly different value here? You see what I'm talking about? I didn't round my temperature. I just plugged that in as my temperature value. So did anybody actually round their temperature? Yeah, you did. What did you get? Do you see your work? Uh-huh. Yeah, I know you got 198 when you rounded. So look at this. I'm going to round to 3, and I will get 198 as well. All right, so remember, these are moles. This is not mass yet. So what are we going to do to these? Convert. Okay, they told you what the gas is. It's nitrogen. So we just need to refresh your memory. What is the formula when you have a gas, like nitrogen, that is not noble? What do you have to do to him? Is it N or is it N2? It's N2. Why is it N2? It's not a noble gas. All right, so coming down here, 1 mole of nitrogen gas. Each nitrogen is 14, so we're going to double that up, 28.0. So I'm going to take this 198, and I'm going to multiply by 28. All right, so my answer on the calculator is 5,544. And that would be grams, right? How many sig figs do you think I'm going to carry along? 3. So I'm going to say 5,540 grams. Now, if you put that in scientific notation, 5.54 times 10 to the 3rd grams. Either of these are perfectly fine. So look at that answer that's online. I did post some answers to selected problems, and I did a typo. I'm sorry. I'll go back and fix it. Okay. All right, so coming right along, I want to show you one more problem, and it is actually number 13. It's the very first problem with the partial pressures. And there's a reason why I selected this one. Okay, so let's have a quick recap of what partial pressure is. When you have a container, and inside of that container, let's say we have like a few different types of gases. It's kind of like the air you're breathing right now. The air you're breathing right now, you actually have a mixture of different gases inside. Does anybody know what the number 1 gas that we are breathing is? It is nitrogen. All right. A lot of people think that for some reason it's like, I don't know, oxygen. I'm like, no. I actually had a student say hydrogen, and I was like, no, we're not combustive. We would all be exploding right now if there was hydrogen gas around us. That'd be a pretty frightening experience. Who knows? Maybe there's a planet out there that is hydrogen, like high hydrogen content in their atmosphere, but not us. All right, each one of these little gases in here is going to be moving around and slamming up against the container. And so all of these little gases are contributing to the total pressure of the system. Now, the tiny little pieces of pressure that each one exerts is what we call partial pressure. That's what partial pressure is. Now, partial pressure is dependent upon how many gas particles of that gas are slamming the container. How many? Now, hey guys, this is kind of a recap, and I'm sorry if this is going to hurt your brain, but we call that moles. All right, partial pressure is dependent upon the number of moles. Is it dependent upon the mass? What did I just say? Is it dependent upon mass? No, because every gas particle has a different molar mass, right? Some of these particles are big, some of these particles are small. It doesn't matter what their size is, it matters how many there are. So remember this. Now, if you've got your notes or whatever, you may want to jot this down. Partial pressure is dependent upon moles. Pressure is dependent upon moles, not mass. All right, now I did present to you guys in one of the previous notes that we have done, I did present this information, but I'm going to refresh your memory. Pressure, partial, like partial pressure, is equal to this fancy X that I call a mole ratio times the total pressure of the system. Now this mole ratio, the thing that you have to know about this guy's value is the mole ratio is always going to be less than 1.0. It's a fraction. It's meant to be a fraction less than 1. And the way that you get your mole ratio is you put the number of moles that of the gas that you're trying to find, of the gas you want, of the gas that you want the partial pressure for, and you divide it by the total number of moles of this system or container. Okay, so this right here is how you calculate the mole ratio. All right, so in question number, I think this is what, 14, am I right, guys? 14? Oh, 13, sorry. In question number 13, they kind of guide you along. In question A, they want you to solve for moles of CO2. In question B, they want you to solve for moles of O2. And then they start asking you about partial pressure. So once you get your moles, you can do a mole ratio and then solve for your total pressure, your partial pressure. All right, ladies and gentlemen, here's one thing I want to ask about you. Hey guys, look at that mole ratio. It's a fraction, right? It is the part over the whole. What is the part over a whole times 100? A percentage. So I want you on your worksheet, look further down after, what is this, question 13? Look down below underneath 13. Yeah, look at these. Do you see 15 and 16? See how they give you percents? Yeah. Guys, all you have to do with a percent is you change it into a decimal. You divide by 100, and then you've got your decimal, and that's a mole fraction, the same thing as a mole fraction. All right, so if you see a percentage, change it into a decimal, and use that decimal in that formula. It's the same thing. All right, so let's go through and let's start answering these, okay? I'm going to start with A. To solve A, let's see, CO2. Looks like there's 152 grams of CO2. Let's change that to moles. Part B, 86 grams of O2. Change that to moles. Let's see, 32 is a molar mass. Okay, can I get a couple answers? I think the first one, I can't remember, I used to have it memorized. What is it? Nice, 3.45, and that would be moles of CO2. And for this one, I think if you want to round to 2 sig figs, it's totally fine. What is it though? 2.7? 2.7 or 2.70, whatever, moles of O2. All right, so let's go into C. C wants you to do the partial pressure of oxygen. So for my mole fraction, you want to put the one that you are trying to solve for on the top. All right, part C wants me to do the partial pressure of oxygen, so I'm going to put this value on the top. So here's my mole fraction. You ready? I'm going to put 2.70 moles over, so we're going to take that and put it over the grand total. So this will be 3.45 plus 2.70. So here's our mole fraction. Now the total pressure of the system is going to be given to you in the problem. The problem says that the total pressure was 365 kPa. All right, so that will help you solve for the partial pressure of oxygen. Let's do the last one. Now I'm going to switch the numerator. I'm going to make sure that the numerator is now 3.45 because that's our CO2. Put it over the grand total again. That would be 3.45 plus 2.70. And do again by multiplying by the total pressure. So 365 kPa. All right, now when you solve for these two partial pressures, when you get those numbers, what will you get when you add them together? What will you get when you add the two partial pressures together? The total pressure, which is 365 kPa. So there you go. All right, make sure that your two answers add up to 365 and then you're set, you're done. Okay? All right, so that was the last practice problem that I'm going to show you in this particular vodcast. There will probably be another vodcast later on. But for now, that's it. And I hope it helped a little bit. All right, you guys, peace out.